Hi. In this lecture, we're going to extend the core idea of the prisoner's dilemma, where it's in my individual benefit to defect, but collectively, we're better off if we cooperate. What I mean by extend is this. In the prisoner's dilemma, it's a two-player game. But more generally, we can think of n-person prisoner's dilemma, where when I cooperate, lots of people benefit, not just one. And what we want to see is how those differ from the standard prisoner's dilemma, and see how those also sort of apply in some real-world cases. So the first thing we're going to talk about is what is called a collective action problem. In a collective action problem, I make some choice. Do I contribute? Now there's a cost to me to contribute, but there's a benefit to everyone else. So how do we write this? We write this as follows. We say let's let xj be the action of person j. And what we'll assume is that xj is some amount of effort. It could be anywhere between 0 and 1. It's how much you're contributing to the public good. Now there's a cost, so the more I contribute xj, the more it costs me. So my payoff is negative in my action. So therefore you think I should choose xj to be 0. And that's sometimes like defecting in the prisoner's dilemma. However, we also assume that there's a benefit, which is the sum. This sign here means the sum. It's the sum of all of the xi's, of all the people in society. So collectively I'd be better off if everybody put in a big xi, that xi be 1, but individually I don't want to. Now what we assume here is we assume this term beta is between 0 and 1. If beta were bigger than 1, that would mean to be my interest to cooperate, because my cost would be minus xj, but then I'd be getting beta times xj, and beta is bigger than 1, so I'd be better off. So we assume that beta is in 0, 1. So my collective benefit from doing this thing is actually less than my individual cost. Let's look at an example. Let's suppose there's 10 people, and we're going to assume that beta is equal to 0.6. Now let's suppose everybody else is cooperating. So let's suppose I'm x1, and that x2 equals x3 equals x10 equals 1. So everybody else is doing 1. So my payoff if I choose x1 equals 0 is just going to equal 0 plus 0.6 times 9, which is 5.4. Because everybody else is cooperating, so there's 9 people cooperating, so I'm going to get 0.6 times that, which is 5.4, which is great. If I were to cooperate, it's going to cost me 1, and what I'm going to get, though, is I'm going to get 0.6 times 10, which is 6, minus 1, which is 5. But 5.4 is bigger than 5, so it's in my interest to put x1 equals 0, but collectively, everybody else would be better off if I would choose x1 equal to 1. So again, this is a lot like the prisoner's dilemma, except for instead of me playing against one person, I'm playing against a whole bunch of other people. Where does this apply? Well, think of things like carbon emissions. It's in our collective interest if we reduce carbon emissions. So if I sort of, put forth effort in order to, put less carbon in the air. But it's costly for me to do that. And so what happens is over time, we've had lots more carbon emissions, probably more than we'd ideally like to have, because it's a collective action problem. Now sometimes these are called free rider problems. They're called free rider because it's in my interest to free ride off the goodwill of everyone else. I'd like everyone else to cooperate, but I don't want to. Now there's another type of sort of n-person prisoner's dilemma, which is called a common pool resource problem. And this differs a little bit from a collective action problem. Let me explain how. In a common pool resource problem, we've got something, let's say like cod in the ocean. And if we fish those too much, the population gets smaller and the population can't reproduce itself. So what we're trying to do is manage some resource that has the possibility of reproducing itself. Let's see how this would work. Let's suppose now that I've got to decide how much cod to eat. And so we'll let xj equal the amount of cod that I eat, or how much I fish out. And we'll let x be the total consumed. That's the sum of what everybody does. And what we'll assume is that the amount of cod available next period is just the cod that was available this period minus what was eaten squared. Because you're going to assume that like cod can, sort of mate and reproduce and make more cod. And so the more we eat, the fewer there are to reproduce. So let's do an example. Let's suppose that the cod population is at 25, and let's suppose that we eat 20. So if we eat 20, then how much is going to be available next period? Well, just 25 minus 20 squared, which is 25. So we've got a nice stable equilibrium here. We're going to have 25 cod this period, 25 cod next period, 25 cod the period after that. Everything's going to be perfectly great. But what if I say, I'm going to have a party, let's have a big cod fest and let's, I'm just going to consume more cod than I'm supposed to. And that's going to drive X1 up to 21. So now collectively, we're eating 21 units of cod. Well, how much are we going to have next time? Well, next time we're going to have 25 minus 21 squared, which is 4 squared, which is 16. Well, if we've got 16, and we've got a problem because in the past we've been eating 20 units of cod, 20 is bigger than 16, we're going to run out, and the cod's all going to go away. Now you might think, okay, that doesn't make any sense, but if we think about it, there's lots of cases of that happening. There's a famous book written by Jared Diamond called Collapse, where he talks exactly about this problem. That you've got a society of people, whether it's the people in Vinland, whether it's people on the, managing cod, whether it's people on Easter Island, and what you get is overfishing, overconsumption, and eventually the resource goes away. So in the case of Easter Island, what you see is the population was getting bigger and bigger and bigger, and then there was a collapse. And the collapse happened when the forests were completely destroyed. They kept sort of harvesting too much wood, and the forests couldn't reproduce themselves, and what happened is you had a collapse of the society. If you look at present-day Philippines, this is a graph showing the total forest cover, and you see that it was very high, and then suddenly it's fallen really, really quickly. Again, over-harvesting of the forest. Now the Philippines, luckily, they're part of the global economy. They can trade for things that they used to get from the forest, but if they were isolated, like the people on Easter Island, they too would have collapsed. In the previous lecture, we talked about, look, we've got all these ways to overcome these things. Repeated games, reputation, networks, group selection, kin selection, incentives, prohibitions, all sorts of stuff that we can do in order to get cooperation. Well, those were for sort of two-person problems in most cases, and they ignored a lot of the particulars. So when you think about cod, that's a very different thing than thinking about forest, and that seems to be a very different thing than, say, cattle grazing on a commons. So when we think about these collective action problems, or these common pool resource problems, we realize that each one in and of itself is particular, and so the way we're going to have to solve it, the way we're going to have to get cooperation, is going to depend on the circumstances of the problem itself. The particulars are going to matter. And that's where we're going to go in the next lecture, to talk about how you solve collective action problems and common pool resource problems in the real world. All right. Thank you.